Today's question is about a math proof. Let g of x be a function that has a second derivative, defined on an open interval that includes the closed interval from a to b, where is less than b. Assume that the limit, as x approaches it from the right, of the difference between g of x and g of a, divided by x minus a, equals 0. Also, assume that g of b is equal to g of a. Prove that there exists at least one point c between a and b where the second derivative of g at c equals 0. Alright, let's take this step by step together. We're told that g of x has a second derivative. That's great, because that automatically means the function is differentiable and also continuous. Now we look at the first condition. The limit as x approaches from the right of the difference between g of x and g of a, divided by x minus a, is 0. What does that mean? Well, that's just the definition of the right-hand derivative at the point a. Since that limit exists and equals 0, and since g of x is differentiable, it means the actual derivative it exists and is equal to 0. So now we know two things. First, the value of the derivative of g at a is 0. Second, the value of g at a is equal to the value of g at b. Now let's think about applying Rolle's theorem. This theorem says that if a function is continuous on a closed interval, differentiable on the open interval, and takes the same value at both ends of the interval, then there must be at least one point in between where the first derivative is 0. All those conditions are satisfied here. G is continuous and differentiable, and it has equal values at the endpoints a and b. So Rolle's theorem tells us that there is some point between a and b, let's call it C1, where the first derivative of g is 0. Now here's the clever part. We already knew that the derivative of g at it is 0. And now we found another point, C1, where the derivative is also 0. That means we can apply Rolle's theorem again, this time to the first derivative of g. Think of g prime, or the first derivative of g, as a new function. That new function is also continuous and differentiable on the interval from a to c1. And it equals 0 at both ends, because we know the derivative at is 0, and the derivative at c1 is 0 too. So by applying Rolle's theorem again, but now to this first derivative function, there must exist a point, let's call it c, between a and c1, where the derivative of the first derivative is 0. But the derivative of the first derivative is just the second derivative. So we've proven that there is a point c between a and b where the second derivative of g is equal to 0. And that's exactly what the question asked us to prove. Now try to picture this. Imagine drawing a smooth hill that starts gently flat at point A, goes up or down a little in the middle, and then ends up exactly level again at point B, same height on both ends. Since the hill starts flat and ends at the same height, and it's smooth the whole way, at some point the curve must bend the other way. That bending change is where the second derivative hits 0. That's the point we just proved must exist. Here are some helpful things to remember when tackling problems like this. 1. If a function's limit of a difference quotient equals 0 at an endpoint, and it's differentiable, then the actual derivative at that point is 0. 2. When a function has equal values at the ends of an interval, and it's smooth enough, Rolle's theorem guarantees a point in the middle where the derivative is 0. 3. If you find two such points where a function or its derivative equals 0, and the function is nicely behaved, you can apply Rolle's theorem again to go one level deeper, to the second derivative. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel and turn on the notification bell. Press the like button. Thank you so much.